Hi everyone, welcome. My name is Jaap Stefels and I'm a machine learning scientist at Adyen.
My name is Itzel Belderbos. I'm also a machine learning scientist at Adyen. And both of us work in credit card fraud. Of course, we try to tackle the fraud and we don't execute the fraud. So we, of course, work with fraud, but we don't have any labels. And today we will tell you everything about it, but let's first get into what Adyen actually does. So suppose today, after PyData, you go home and you want to order an Uber. Sometimes this payment goes through Adyen. So then Uber will send this payment to Adyen. And then we are the payment processing provider, a very expensive word to just say that we do certain stuff with the payment. And then we will send it to the bank of use. This bank can be ING, Revolut, whatever bank you are using. And of course, we assume that most of you are no fraudsters, right? You have good intentions, so your payment will probably be approved. So this is the happy path. But it's also possible that we are dealing with a fraudster. And this fraudster doesn't have good intentions, right? And in that case, we would like the bank oftentimes to decline this payment. But of course, we are the middleman. So it is our responsibility to already decline this payment before it arrives at the bank. So this is where we are living, in the middle. So our model does scores hundreds of transactions per second and even millions per hour.
Millions per hour, you're saying? That means if I make an online transaction right now, so doing online shopping, booking an Uber, or buying groceries online, our model probably scores it?
Yes, that's correct. So
Very
today we will guide you through this whole process, how we implemented this model, and the key takeaways. So let's get into it.
Yes, so that was the more dry stuff. So let's now look at some fraud. So over the past few years, we've seen a steady incline in the number of fraudulent transactions. We're even expecting that 43 billion US dollars will be lost by the end of 2028 due to credit card fraud in general. 43 billion US dollars will be lost. Itzel, do you know how much 43 billion actually is?
Yeah, I'm seeing a lot of zeros, that's for sure. But let's compare this a little bit to put this into perspective. So this is 12 times the revenue of OpenAI. It's 18 times the revenue of Adyen. And we could have bought 100 million PyData tickets with this amount of money. So that means that we could have bought tickets for everybody in the Netherlands and everybody in Germany.
I can see some people from the organization in the front. Can we do 100 million people next year? Yes? OK, let's aim for that then. So given that there's so much money to be earned with credit card fraud in general, and given that everyone in the room is pretty tech savvy, please don't try to do credit card fraud yourself. But if you want to, we'll show you exactly how you can do card testing fraud. Card testing fraud is a type of fraud that we specialize into. And in card testing, the fraudster tries to run a script, and they iterate over details, card combinations, and they're trying to brute force their way into verified card details. So let's see how we can do it. You start off with a desktop, or any device will do, any tablet, any laptop, any computer, even your iPad or your, I don't know, any device will do that connects to the internet. And as the first step, you set up your script. And this script iterates over possible card details. So in this example, you see that the fraudster tries certain card numbers, certain CVC codes, also certain cardholder names as well. And they're trying to iterate over these details until they've found something that matches up, and those details are correct. So as a second step, they run this script on their favorite merchant. And a merchant can be any company that processes their payments through us, Adyen, so Uber or any other company as well. And they do these transactions one by one. And at every transaction, they'll get a response back from the bank, whether a transaction was refused by the bank or whether it was approved by the bank. And of course, our model should block this fraud. Let's assume that we did not block this and we get these responses back. So any approved transaction here means that card combinations are correct. So as step number 3, they can collect all of these card details into one big list, and they can sell this to their fraudulent friends, or they can use it themselves to often buy more expensive goods at a later moment. So they buy a nice headphone or a nice new laptop for themselves. So in this case, they've replaced their desktop with a nice Apple MacBook. Nice, right?
Very nice.
Very nice. No, it's not nice. We don't like this kind of fraud. And there are a few reasons why everyone in this room should care about this kind of fraud. So first of all, anyone in the room, your card details can get stolen this way. If they iterate long enough, they can find your card details as well. So you are all not safe if we do not stop it, right? Second, also the merchant, so the company that processes their payments through Adyen, has to pay a small fee per transaction if you send the amount or the transaction to the bank. So it can be a few cents, but if we see sometimes millions and millions of transactions being fired up, this can add up really, really quickly, especially for smaller merchants. They can simply get attacked, and then suddenly they have to pay like 50, 100K in fines or in transactional fees to Visa or MasterCard. So that's not nice either, right? And thirdly, we at Adyen do not like this kind of fraud because we have also laws and regulations that apply to us. If we send through too much fraud, we can get fines as well, like very big fines. So you don't want this because your card details can get stolen, the merchant has to pay fees, and thirdly, we at Adyen don't like this either. So bad fraud. So we want to prevent it, right?
Yes.
And as clever the fraudster might seem in this use case, they're always leaving their marks in the data. So often what they're doing is they use a certain VPN, which is an IP address for 20, 30, 50 transactions, switch to another one. Or they use a certain pattern in their email address and then switch to another one. So they always have some kind of thing that we can use to identify them. So why not set up just static rules? For example, if you see an IP address 10 times, we start blocking. Like that could work, right?
Yeah, I think I like the suggestion. It's start simple, right? But I think we shouldn't forget that fraudsters are very fast. They iterate their script continuously. They see that we start to block certain patterns, and then they can just simply change the script, right? So I think we need something that's able to learn from mistakes, something more generalizable.
Machine learning, right?
Yes.
Yes.
I think ML would really fit in our use case. But I think that there's still something that we're missing because we don't have any labels. So of course, we do have some sort of indication that something out of the ordinary is going on. We see a huge spike in declines, or we see some weirdly generated emails, but there's no ground truth to it. There's no entity or merchant or even a customer that tells us that a transaction was part of an attack. So we could come up with this ourselves. But we could also go for unsupervised learning, right? So eventually, in our use case, we chose for proxy labels. So we generate these labels ourselves. Let's go over the machine learning iteration cycle to loop you through our thought process. So let's start with the training. We start training our model, and we can also choose for unsupervised learning, right? For maybe some sort of clustering. And when we start this clustering, we see clusters starting to emerge, but we're never sure that these clusters are actually fraud clusters. Maybe we're clustering something completely different. So proxy labels enable for us to have a target and that we know what we're optimizing for. So in this case, proxy labels are very beneficial for us. Then we have trained our model, and then we go towards the evaluation. We have different models, and we would like to compare which model is actually my best model. And we can do this with, of course, metrics. So we need to make our evaluation measurable by means of, for example, false positive rate, true positive rate, you name it. And proxy labels enable this for us. So we found our best model, we're happy with it, and we would now like to deploy it into production. So at the moment, it's just scoring hundreds of transactions per second, but then we start to get questions, right, from the merchant or maybe from a customer, why is this blocked? And we need to be able to explain this. And this explainability is way easier when we have labels. And then the last step, we don't want to stand still. We want to iterate on our model. We want to improve our model. And we can do that looking at different areas of underperformance by means of these proxy labels. And then the loop goes on.
OK, it looks like we need proxy labels. So let's dive into the method that we actually used to define our proxy labeling system. Before that, let's look at some examples here. So these are two merchants, merchant A and merchant B. And one of these merchants is having a nice summer sale, and I think they gave 50% of all their clothing articles. And one of these merchants is having a not so nice day. They are under attack, right? This is not nice. And by simply looking at the volume, you cannot really see whether merchant A has a summer sale or merchant B has a summer sale. But once we start adding approval and refusal information to the mix, it becomes quite obvious that merchant A had a lot of their transactions approved, and therefore it's most likely not a scripted attack. When fraudsters run this script, most of the transactions will be refused because they cannot crack the code yet. So merchant B here is under attack. But these are two pretty simple examples still. Like, it's quite obvious to design a proxy labeling system based on this. Why not just take all the refusals for certain spikes and label these as being an attack? Like, we cannot do this. And for that, we have to look at merchant C. And merchant C is a subscription-based merchant. They're selling subscriptions, just like Netflix. And they also had a bad week. So in the beginning, you can see nice periodic traffic, like more transactions during the day, less transactions during the night. And then boom, the fraudster starts with their attack. And you can see that they're slowly ramping up the volume here. They're becoming more confident. And we see a lot of these spikes happening. Maybe stop this for a second. Yes. And here you can see something different compared to the previous two examples. In this type of fraud, it's not so obvious where the start is and where the end is. It really blends into the normal merchant data. And additionally, we see that this fraudster maybe had some inside information to certain card numbers. Also sometimes possible. Sometimes they have friends working at a certain bank, passing them parts of card numbers as well. And here you can see it by having more approved transactions here as well. You can see quite some volume of approvals as well. So to design a proxy labeling system, we also need to filter this out a bit more. So Itzel, just looking at this kind of fraud, or at this merchant, how would you design a naive approach of a proxy labeling system?
Yeah, looking at this, I see a few clear spikes, right? But I also keep in mind that we're working with real merchant data, and we don't want to overblock for them. We don't want to have any complaints. So I would go for high precision and be very precise. A bit like this.
Sure, but then we would only label the most obvious spikes, right? We would only get the most biggest spikes. So couldn't we just increase the windows a bit and label all of these refused transactions?
Yeah, that's a good point. I mean, if you want to go for a high coverage, you can choose like a broader interval. But I see still an issue with this, because how do we now define the division between attack traffic and non-attack traffic? I think we need something more fine-grained, right?
Sounds good.
And that's why we came up with this proxy labeling strategy. This is a two-step approach that starts with something called temporal anomaly detection. That's a lot of expensive words just to say that we're searching for the intervals in which we suspect there is an attack going on. And this tells us where to look. So where to look, that means we can go for a high recall. And then we have the second step, where we have the graph-based pattern detection. And here we have the more fine-grained step. We look at interactions between different transactions to see how they correlate towards each other. And we can find patterns by means of graphs. And this enables us to be more precise. So let's get into it. Let's look at our time series that we've already seen in a previous example. And we want to filter out areas in which we suspect that there's an attack going on. To do this, we can look at historical transactions. and slap some statistics on them, maybe some percentiles, standard deviations, you name it. And then we can come up with expected transactions. And this already looks way nicer, right? Oh, sorry. This already looks way nicer. We see the clean seasonality. It looks way healthier. And what we can already do is derive some insights from this, because we can look at some ratios. We can look at the ratio between the decline traffic and the expected decline traffic. And this is expected to be high in areas where there might be an attack going on. But we can take it a step further and subtract these from each other. And when we do this, we get the extra transactions, so the excess. And this is very nice, because suppose a merchant has a sale going on. Then they have a huge excess of transactions, but probably most of it is approved, right? And here we clearly see that the largest proportion of transactions is declined. So I think we have found our intervals. Jaap, can you work with this?
I think we can. We must, right? So to understand how we now use this information of where to look to really split the normal data from the merchant from the abnormal data of the merchant, we have to think of a transaction in a bit of a different way. A transaction can also be visualized as a graph where the node, like the middle node, is just the transaction, and around it are all different nodes that characterize a transaction. So in this simple use case, the transaction amount was 0, but we might also have identifiers as time spent on a certain page during the checkout process, or patterns within email addresses. Like, we're not telling you, of course, which identifiers we're using, because then you could probably circumvent our entire proxy labeling system. But say amount is the identifier here that the attacker is using. And say we add more transactions to this graph, we can start linking these transactions based on their identifiers. Nice. And here we are making the assumption, if you paid attention in the beginning, that fraudsters always leave their mark in our data. So for example, they use the same IP address 20, 30, 50 times, or they use a certain pattern in the email address. So by exploiting this in a graph structure, we can find connected components and clusters of transactions. So eventually it will look something like this, and this looks a bit like a chemistry molecule, but it's a representation of a graph here. And here you can see two big clusters, but also some lingering transactions around it, and these transactions around it are not really part of the attack probably. They are just normal transactions made by you guys, for example. So we can remove them based on like degree or density. And then we're left with two nice clusters, cleaned clusters. And here, one of the clusters is centered around the amount, so the simplification that we just gave about our identifiers. But in practice, of course, these clusters will be centered around many identifiers, all connecting to each other. It will be more like an interconnecting connected component, if that makes sense. But we also see another cluster here, where cardholder name is Tina TensorFlow. And Itzel, do you think Tina TensorFlow is also part of the attack?
Yeah, it's hard to tell from this graph, because of course we see a cluster being formed, so I think it could be part of the attack. But it could also be that Tina TensorFlow is just someone who has their own shop, and she doesn't really know how well to integrate with Adyen. And just out of privacy reasons, she just sends her own name for all of her payments. We don't know.
Yes, and this is some issue that we are often seeing. Merchants are often sending us wrong information. So they send their own IP, local host IP, as their IP of all the transactions that they're seeing. Or they're sending their own merchant name as the cardholder name for all transactions. And this might come because they don't have good integrations, which can happen for smaller merchants. They don't really understand how to integrate properly sometimes. But often it's because of privacy reasons, and they don't want to share this information with us. It harms the performance of our clustering, of course, but yes, sometimes they want this. But we need to discriminate between these two cases, whether something is all being linked because it's part of an attack, or it's all being linked because there's a placeholder or static value. And we can simply do this by running the algorithm twice. So these are the spikes that Itzel just mentioned, but we can also do the opposite. We can also look outside of the spikes in only the approved transactions. Because the approved transactions will be very likely normal transactions for a merchant. They will be the normal behavior of a merchant. And we can run the whole algorithm, see which clusters are forming around which kind of identifiers. For example, cart will name Tina TensorFlow in this example. And then, as a second step within this, we can just remove all of these identifiers from the graph we construct on the refused payments inside of the spike. And the refused payments here are very likely to be part of an attack. And by removing these static values, we end up with very certain attack patterns, such as the amount being 0 here. And once we know the pattern, we can use this. This is the actual example for this merchant. Of course, it was not amount, but we can use it to discriminate between attack transactions that we can now label very cleanly and the normal traffic of a merchant. And as you can see, we have done it well, right? We have separated pretty clearly, so let's put it in production. Let's roll it out, right?
No.
Oh.
I think we're missing something. Like, it looks very nice and it looks trustworthy, but like we said in the beginning, we don't have any true labels, right? So now with these proxy labels, we can easily evaluate the performance of our model, but we cannot evaluate the performance of these labels. So that's an issue. So luckily within Adyen, we came up with a solution to this, and that is the ground truth dataset. And this is a large and diverse data set consisting of different geographical areas, different merchants, different time frames. And this we've constructed together by labeling all together with domain experts. And, well, we were happy to find a very good performance on this ground truth data set. We found 100% precision and approximately 97% recall. So this looks very nice, right, Jaap?
Yeah, let's put it in production now.
Oh.
Oh.
So we're still missing something. So this ground truth data set is, of course, a subset of all of the labeled transactions labeled by our proxy labeling system. So there's still some manual steps here that we need to take. We still need to investigate these cases that are outside of the ground truth data set, and that, yeah, we still need to validate what is going on with these cases. And fortunately, we found also good results for these. So I think now we could put into production, right?
No, we're still missing something else. We don't have any visibility about all of the attacks that happen on our platform. Like, our proxy labeling system only labels a subset of all of the attacks that happen. So these are the false negatives by our system. And these are the most difficult cases to extract from your new proxy labeling system. And because you do not have any visibility of these cases. So what we did was we set up a feedback loop where people that use our product or model or look at our data, we have many domain experts working in our company that work for fraud domain, they can give us feedback whether they have not seen an attack in our labeling system or whether they have seen an attack in a labeling system that shouldn't be there. And by incorporating this feedback loop, we can always update our ground truth test set with the newest and latest trends in fraud. And this way we keep our ground truth test set always diverse and unbiased this way. So doing the three-step approach, first ground truth test set, you can always calculate coverage of any new system. You need this data set. Second, the additional output of the model, you can look at a few examples, a few hundred, and see if these make sense, if there are any false positives in here. And then lastly, you need an evaluation system for the cases that you are not aware of. We can now put it in production. And we did. So the story here is, of course, not really about our proxy labeling system. It's more about you guys, right? Like, this proxy labeling system is, of course, a simplification of what we actually run in production, and we have multiple proxy labeling systems for this specific use case. But if you really want to go 10x with your model performance, you need to follow these three takeaways. So first of all, always apply your domain knowledge to the problem. And why are we saying this? Like, originally when we started out, we always looked into academic papers as well. We used embeddings, VAEs, autoencoders, all kinds of more complex systems. But eventually what worked best for our use case was not applying some generic academic example, but really looking into our data, understanding that there was a relationship between transactions, that we could link on these transactions, for example, IP address, and applying that into our proxy labeling system. So by using your domain knowledge, you can achieve far better results compared to any other system.
Yes, another important point is that you need to be able to trust your label. And that's something that we also encountered in the beginning. We were iterating on our model really fast, but we never really trusted the model because we saw good performance, but we weren't really sure if the labels that we at the moment had, that they were correct. Your model is only as good as your data, so make sure that you have a good evaluation system in place.
Sounds good. And lastly, keep it simple. And this might sound obvious, but ML is already a black box. And if you put another black box before it, it's very difficult to see the overperformance or the underperformance, to understand why your ML model is suddenly performing better or worse than you're expecting. If you have a very intuitive and interpretable proxy labeling system, it's really easy to understand where this uplift is coming from. So by keeping it simple, you can explain it also to your other stakeholders in the company as well. And you can explain to yourself where this uplift is coming from. So these are the key takeaways that we want to give to you if you ever feel tempted to design a proxy labeling system for any unsupervised problem in your company as well. Thanks.
Yeah, and if one takeaway that we want you to bring home is if you order your Uber today or maybe another day, make sure that, or be aware that we are watching. Thank you.
Wow, yeah, thank you so much for this amazing talk. It was very engaging, amazing chemistry. I almost felt like I'm a detective looking for fraudsters. But I guess some of you might have questions. So this is time for the Q&A. Let's start in the front.
Hi, thank you for your talk. So the question is, have you tried isolation forest instead of graph-based neural network? Because graph-based is looking quite difficult to implement for your use case. So did you compare with some simple model?
So isolation forest, don't you need labels for that?
No, it's unsupervised.
Okay, no, we haven't
I
tried
think
it.
we looked into that. I think we ran an experiment in this initial setup. I don't think that we saw uplift compared to the system that we've now explained to you.
Yeah. Okay, thanks.
And also, maybe it's good to understand that fraudsters, is their job essentially to blend into the normal traffic of the merchant, right? They do their best to make everything look as more likely to be part of the traffic. So if in isolation forest, it's sometimes really difficult to isolate this from the data there. And therefore, a graph-based solution would work better.
Right, let's move a little bit further back. I see a hand there.
Thanks very much for your talk. I have two questions. My first question is if you could say a bit more about how you balance between detecting fraud versus not being able to fulfill an actual purchase. I think both are harmful for ADN, so I would love to hear more about that. And then the second thing I'm wondering, but maybe this is a silly question, where is two-factor authentication with these credit cards? Wouldn't that solve a big piece of the puzzle? Thanks.
Do you want to take the first, I take the second?
Yeah, that's a good point. Of course, there's a lot of collaboration going on with another team, the more optimization team. But of course, our team as a fraud team is not to optimize the conversion rate, as you call that, so the authorization rate. Our goal is just to catch as much fraud as possible and, of course, not to harm the merchant. So it's more of a false positive rate balance, false positive rate and, of course, recall. So I think also, in a way, it's not on us only. We are just a data scientist, so we're continuously in conversation also with product managers, account managers, and with the merchant in what they find what I find reasonable. And you wanted to take next?
Yes, I can do it. We already discussed it actually when we were practicing, like might this question come up, because it's a very valid point, and thank you for asking. In Europe, it's quite common to have two-factor authentication, but it's not as common in the United States, for example. Like once you start enforcing this a lot, people will drop off very quickly. So it's a trade-off between doing this. You can, for example, you could mitigate this type of fraud by always applying 3DS, we call it, two-factor authentication, but then a lot of people would stop with the transaction. So often, if we are very sure that something is very not likely to be fraud, we'll still pass it forward, because we do not always want to apply this, like even in the EU as well. Does it answer your question? Yes. Great.
Okay, we can just move forward, yeah.
Hi, thanks for your talk. The only thing I'm wondering, could you tell us a bit more about that ground truth data set that you referred to validate the proxy labels you had created? I'm not sure I fully followed that part.
Yes, we can describe how we did it. We set up a framework where people could manually label these transactions. So any person that is communicating to the merchants, they have a system that they can say that these transactions were very certain to be part of a scripted attack or not, and these transactions were very certain to be not part of a card testing scripted attack or not. So this forms our ground truth test set with gold standard labels that we can use for this purpose.
Yeah, and also for this, we set up an alerting system as well. Because, of course, if you just randomly start labeling transactions, you might not have a very diverse data set. So we do have some alerting, or maybe account managers that label some transactions for us, or say, hey, maybe you need to take a look at this merchant. So yeah, it's a bit of a combination of different things. So I think good communication is important, such that you have all your information available. Yeah, I don't know if that answers your question, or if you were more curious about the content.
No, makes sense, thanks.
There are more questions? Okay, I want to include some people from the back. Please raise your hand again.
Hi, thanks for the wonderful presentation. I just wanted to check bias in that you're getting a feedback loop specifically related to your rejected transactions. How do you control bias in that feedback loop?
That's an excellent question. We try to mitigate this bias by always making sure that there are other people outside of us also notifying us when they see an attack that's not yet incorporated into this ground truth test set. Or do you mean the bias of also training our models on top of this as well?
No, on the proxy data set. So how do you control bias in that? Yeah.
Yes, so by having domain experts, people who look at fraud every day, they can look at the output of the system. They can say very clearly, like, this is now in the system, this is not in the system. If it's not in the system, we should immediately act upon this, because this is an indication that the identifier set that we're using for this graph-based part maybe isn't sufficing for this problem, right? Or that there are other limitations to the system. So we take these cases very seriously and try to immediately act upon it to mitigate the bias as best as we can.
And actually, a funny story is that when we had our ground truth data set and we started to validate it with this proxy labeling system, we even found 2 cases in which our ground truth hand-labeled case was actually not fully correct, and our system kind of caught it. So that's also a nice find.
Thank you.
We have one more question. There was in the front very patiently waiting for me, and I kept ignoring him, but now I want to give the time. But of course, I think you are available after the talk a little bit.
Yes, we will be here.
So don't worry.
Thanks for the talk. As a Fraudster 101, make sure I understand, would it make sense to slowly increase the number of attacks that I make? Because then in this case, I will not have the spike, and it will probably go into the trend, so it will not be accounted for. Do I understand that correctly, or am I missing something?
We look at different windows when trying to do the spike detection as well. Like we're not only doing a single offset between what's normal for the merchant. If we increase it long enough, this might also become obvious to our system as well.
Not a short-term car switch then, thank you.
It's a very good find, yes. We've thought of this as well. Yeah.
All right, thank you everyone, and thank you for this amazing talk. Give it up one more time for Jaap and Itzel.